Hello everyone. This is the paper presentation of Group 8 for CS 643 Cloud Computing class. Our topic is Customizable and Extensible Deployment for Mobile Cloud Applications. These are the authors who actually wrote the paper, and these authors are from University of Washington. The presenters are Rajveer Sidhu and myself, Zareen Khan. The main topics that we are gonna cover in this presentation is the motivation. What is the key motivation behind Sapphire? Sapphire. The main topic of presentation here is Sapphire, and we will learn about it as we go further. The design architecture of Sapphire, and discuss mainly the two blocks of the design diagram, that's deployment kernel and deployment manager. The programming model of Sapphire, a design example. We will also see one of the implementation. And then we are going to discuss the experiments and the results and evaluations based on the experiments, and finally the conclusion. Now let us discuss what is the main motivation and the requirement actually. In today's modern application, it faces new challenges in managing today's highly distributed and heterogeneous environment. Somehow, the programmer actually needs to stitch together a code that can span over different devices like smartphones, tablets, computers, and personal devices. Needs to be integrated with cloud. And also, the programmers need to make important deployment decisions. To address those challenges, programmers must have to make some distributed deployment decisions. The main three questions that needs to be answered by the programmers are: where data and computation should be located, where data should be replicated or cached, what kind of data consistency level is needed. Now, the answers to the above three questions also depends on application requirements. And sometimes they have to mix application deployment decisions with complex application logic. Today's applications is spread over many heterogeneous platforms, and they have to communicate and share data. Simple applications can communicate easily, like using just a single common MySQL database. But complex application needs to use services like SOAP, REST, Sapphire, Thrift, etc. to communicate shared data and logic. So Sapphire can actually integrate them and subsume most of their functions itself. Sapphire. This paper presents Sapphire, a distributed and flexible platform. Sapphire facilitates the management and deployment of applications spanning over a wide variety of devices like computers, mobiles, tablets, and cloud. Design architecture of Sapphire looks as follows. There are three layers. Let's start with the bottom layer. The bottom layer is the deployment kernel, the deployment management layer. The DMs are actually here, the deployment managers. And the top layer is the Sapphire application. And basically, this is where the application code sits in here, which consists of different classes and Sapphire objects, etc. Now, Let us see what these three layers actually in detail. At bottom layer, Sapphire's deployment kernel integrates heterogeneous mobile devices and cloud servers. Deployment layer, it sits between the kernel and the application. It is collection of pluggable deployment management modules that extend the kernel to support application specific needs. Application layer. It is the layer where actual application code sits. Sapphire objects. A Sapphire application is basically, it consists of the client side and server side applications, and both the client side and server side application consist of Sapphire objects. Sapphire objects share common logical address so that they can invoke each other through simple location independent calls. This is the key point here, that SOs share common logical address. The bottom layer is the deployment kernel layer, which is flexible and extensible runtime system. It provides only the most basic distribution functions, including Sapphire object addressing and location tracking, best effort RPC based communication, Sapphire object migration, and basic resource management. It actually resembles like an IP service. Now let us see deployment managers in detail. As compared to the deployment kernel, the deployment managers actually provides you with more complex functionality, but deployment managers are actually the extension of deployment kernel with more complex functionalities. Each Sapphire object can have an attached deployment manager which provides runtime distribution. A programmer chooses deployment manager to customize behavior. Like, let's take an example to choose a deployment manager to increase fault tolerance. Deployment managers, as pointed out earlier, customize and control the behavior of individual Sapphire objects in the distributed mobile cloud environment. The development kernels provide direct API support for the DMs. The deployment kernel does all the heavy lifting, while the deployment managers simply tell the deployment kernel what to lift through the deployment kernel's API. There is also deployment managers library that provides for many management features. The structure of deployment manager and its API are as follows. The main three key components here to notice is the proxy, the instance manager, and the coordinator. The proxy is basically responsible for caller side tasks like routing method calls. The key responsibility of instance manager is the callee side task like keeping replicas of the Sapphire objects synchronized. The coordinator. The key task responsibility of coordinator is for centralized tasks such as failure handling. All the components are optional. This is a programming model example Sapphire object from Bluebird. As you see, there is a user class uses consistent hashing. Then there is a variable string username. and so on. And we will get to learn this in more detail in the following slides. Sapphire has an object-based programming model wherein Sapphire objects are key programming abstraction for managing application code and data locality. A programmer can define Sapphire objects using a Sapphire class declaration instead of standard class declaration, as seen in sample code. Each Sapphire object will have its code and data on same virtual node. Calling Sapphire objects. Sapphire objects communicate using method invocation. Invocation is location independent and symmetric, means it can occur from mobile device to server, from server to device, from device to device, or between servers in cloud. Deployment managers help to handle failures on behalf of Sapphire objects. Sapphire objects are passed by reference. All other arguments and return values from Sapphire object invocations are passed by value. Choosing deployment managers. Programmers employ the uses keyword to specify a deployment manager when defining a Sapphire object. For example, in code snippet of Bluebird, the Sapphire class declaration binds the consistent caching deployment manager to the user class. In this case, every instance of user created by the program will have the consistent caching DM attached to it, as we can go back and see. The consistent caching DM actually is attached to class user using the keyword uses. Sapphire provides a library of standard deployment managers. Additionally, deployment managers are extensible. Each Sapphire object can have only one deployment manager, and each instance of the Sapphire object must use the same deployment manager. Deployment Manager API. The deployment kernel involves deployment managers using upcalls. Each component receives a different set of upcalls like onCreate, onRPC, etc. In each upcall, the deployment manager component can perform various management tasks on the Sapphire objects using a set of primitives like invoke RPC, get node, etc. Finally, the deployment kernel also instantiates one coordinator for each deployment manager instance. The OTS manages the coordinators. DM design examples. There are many classes of DM design, and we are going to discuss three of them as listed below. Code offloading, peer-to-peer, and replication. The code offloading deployment managers are actually useful for computing intensive applications. Peer-to-peer. They support the direct sharing of Sapphire objects across client mobile devices without needing to go through the cloud. Replication. As the name suggests, the Sapphire library contains three replication deployment managers that replicates the Sapphire object across several servers for fault tolerance. The implementation, Sapphire application and runtime system. The authors built deployment kernel prototype using Java to support Android. Implementation. Now, altogether, the deployment kernel consists of 12,735 lines, including 10,912 lines of Apache Harmony code. Java 1.6.0-38 Java Virtual Machine was used to run Sapphire in cluster, while tablets and phones ran Sapphire on Android. Java RMI was used for low-level RPCs between deployment kernel nodes. The prototype does not support secure communication between deployment kernel servers. Now let us discuss what experiments were done and its evaluation. The authors describe their experience building new applications based on following three objectives. The first one is development ease. It took relatively little time and programming experience to develop Sapphire applications. In particular, Deployment Manager library provides for most of this ease. They did not have to handle code failures because the code offload deployment manager hides them and manages itself. Even the largest application, Twitter clone, Bluebird, was implemented in under 800 lines. Isn't that great? The second point is the deployment flexibility. Changing an Sapphire object's deployment manager, which changes its distribution, requires only a one-line code change. The authors made use of this property throughout their prototype developments. The third point here is the management code generality. Authors applied several deployment managers to multiple Sapphire objects within individual and across applications. With Bluebird, which had 10 Sapphire objects, author could reuse several of deployment managers. Now let us discuss the experimental setup that was set actually and its results. The experiments were performed on a homogeneous cluster of server machines and several types of devices like tablets and phones. Each server contained two quad-core Intel Xeon E5335 2 GHz CPUs with 8 GB DRAM running Ubuntu 12.04. The devices were Nexus tablets running on 1.3 GHz Hummingbird processor and 1 GB DRAM. Nexus smartphones were with the 1 GHz single-core processor with 512 MB of DRAM. The devices were located on same local area network as the servers. Now the micro benchmarks and the results of the experiments are as follows. The RPC latency comparison. Authors compared Sapphire RPC to Java RMI and to REST and Thrift. While Thrift was generally faster in all cases, Java RMI and Sapphire were comparable and were faster than REST. Even Sapphire was faster than REST without optimizations. The following is the RPC latency comparison table. Request latencies in milliseconds for local, server to server, tablet to server, server to tablet, and tablet to tablet. Note that REST does not support communication to tablets, as you would see these are dashed out. Now, if you see let us first look at the local latencies for each of the protocols. For Sapphire, you will see the latency is 0.08. For Java RMI, it is 0.05. For Thrift, it is 0.04. And for REST, it is 0.49. So, Thrift is faster than Java, RMI, and Sapphire. Java, RMI, and Sapphire are comparable, but definitely Sapphire is way faster than rest when you compare 0.08 versus 0.49. Now let us take the case of server to server. For Sapphire, the latency is 0.16, for Java RMI it is 0.12, and for Thrift it is 0.11. And again, as you see, the latency for REST is 0.64, which is way more as compared to Sapphire, which is 0.16. From tablet to server here. Again, the Sapphire is 5.9, Java RMI is 4.6, Thrift is 2.0, and REST is 7.9. And again, you will see that Sapphire is much better than REST, but is almost comparable to Java RMI. And again, Thrift is always faster in all these cases. But for server to tablet, Sapphire is 3.4, which is not so bad as compared to Java RMI and Thrift, which is 2.0. But for tablet to tablet, you will see that the latency for Sapphire is 12.0, for Java RMI it is 7.2, and for Thrift it is 3.6. And in this case, you will see that the difference is a little like not so much comparable, but still if it is better if you see in this case for local, where the comparison for Sapphire and REST is like in terms of multiplication of 5. The throughput comparison. Authors measured throughput for Sapphire deployment kernel and Java RMI. Java RMI's object throughput was 15% higher. This is because Sapphire's null RPCs are not truly empty. They carry the serialized structure telling deployment kernel how to direct the call. To break the cost further, authors compared again with Java RMI carrying some dummy payload identical to Sapphire's null RPCs. It reduced the difference to 3.6% as compared to 15%. This additional cost is the serialization cost for dispatching structure. As you will see below, the chart of throughput comparison between Sapphire deployment kernel and Java RMI. The red graph here is for Java RMI null RPC, and the green graph here is for the Sapphire null RPC. And you will see that on the y-axis we have request per s, and on the x-axis we have clients. The cost is on the y-axis and the number of clients is on the x-axis. Now let us conclude the topic. Sapphire simplifies the development of mobile cloud applications. Sapphire greatly eases the programming of heterogeneous distributed cloud mobile applications. It provides great flexibility in choosing and changing deployment decisions. It gives programmers fine-grained control over performance, availability, and scalability. I would like to thank you all for your time. Thank you. Take care. Bye.